Right, so I'm calling my talk Eigenvalues as I Like Them. And I'm going to go through a lot of introductory material that all my previous speakers have mentioned, but perhaps with a different perspective. So let's look at this ballet dancer, ballerina, who is doing a pirouette. And there is one axis, the vertical axis, through her centroid that remains fixed. So that's an eigenvector. And here, the ballerina can return to her position, although we already said rotation does not correspond always to eigenvalues. But let's say she remained the same and the eigenvalue is therefore 1. Now, let's change the transformation A, and we apply this A to the same ballet dancer, but something bad for her happens, that she searches for we represent this by AX. A is the transformation applied to the ballet dancer, going to 2x, twice her size along the x-axis. Now, what does a linear transformation do to a vector? So let's consider this matrix, which is a rotation of 90 degrees. The first column is cos 90 degrees sine 90, and the second column is minus sine 90 cos 90. So when you apply this to a vector, actually cos 90, as you know, is 0, sine 90 is 1. So actually we have a very simple 0, 1, minus 1 matrix operated on A1, A2. What happens to A1, A2? Does it turn to 90 degrees? Not actually. It's minus A2, A1. And from, so what we get is, and I should have written that actually as a column, not a row. So I need to do transpose there. So for example, if you have 3, 4, and you rotate by 90 degrees, you get minus 4, 3, okay? Where that is the origin. Now, eigenvectors are these vectors that remain as they are after the transformation, but may be stretched or reduced by a factor. So let's take this matrix, which is a very simple 2 by 2 matrix. First column is 3, 0, second column is 1, 2, and over here, the green vector shows 3, 0, and the yellow vector shows another vector, because here 3, 0 there gives me an eigenvalue of 3 with an eigenvector of I, what was referred to as I in previous talks, the unit vector along the x-axis. But we also have another eigenvector, which is minus 1, 1, and we have a stretch of 2 over there. So what happens to a general vector? A general vector, so if you have a vector somewhere in the middle there, it is influenced by both effects. And you get both the stretch along the x-axis and the stretch along the minus 1, 1. So I know you've seen this by now. You're experts on the eigenvalue equation. You have the transformation matrix A operated on an eigenvector V. You get an eigenvalue lambda, and V is not 0, because if V is 0, obviously A operated on 0 always gives me 0, so that's always true. So if I want an eigenvalue lambda with V, which is not 0, that is a solution of the eigenvalue equation, right? So as you've seen previously by many of the in many of the other talks, you can rewrite this as A minus lambda I V equals 0. And if I want V not to be 0, this means that the solution is not unique. If the solution is not unique of this system of equations, because when you open this up, you get a system of equations. If the matrix A is, for example, 3 by 3, you're going to get 3 equations, right? Which are, in a sense, homogeneous because you have 0 there. And I want V not to be 0, but I know that this matrix multiplied by 0 gives me 0, so the solution is not unique. Therefore, the matrix is not invertible. And as you know, if matrices are not invertible, their determinant is 0. So solving determinant equals 0 is an inverse problem. Why? We have sort of here 2 unknowns, lambda and V. So what you can do is to, over here, I am drawing these axes, which are the columns, right? So over here, I have 3 minus 0.8, 0, that would be one direction, and 1, 2 minus 0.8, which would be 1.2, another direction. Anyway, you get a parallelogram, which has an area equal to 2.64. As that parallelogram, okay, reduces in area until the area is 0, you hit an eigenvalue. So what we're doing here is we are going through various values of lambda until the determinant is 0. When we do that, the line containing the whole parallelogram, which now has area 0, will be the eigenvector. So this was shown even by Adriana very nicely. And until you get the eigenvalue, when you get the eigenvalue, the area becomes 0. So the solution of this equation, by the way, the eigenvalues are our natural modes of vibration. So the eigenvectors with eigenvalue 2, okay, will be along the yellow line, and the eigenvectors with eigenvalue 3 will be along the green line. And when that matrix, that transformation, which could be a rotation, a reflection, a shear, is applied to a system, then it will transform any vector in the system along the 2 directions shown here. Right, so let's go to quantum mechanics, which Professor Sciriha has so nicely explained. Schrodinger's time-independent equation for a delocalized electron in a molecule, what do we mean? For example, if you take benzene, benzene has 6 carbon atoms, and here we have a picture of the 6 carbon atoms, okay, joined in a hexagon, okay? The lines between 2 carbon atoms would be the bonds of the benzene, okay? The bonds between the carbon atoms. Now, when we apply H psi equals Z psi, which is an approximation of the Schrodinger's equation, assuming that the orbitals, that is the cloud occupied by electrons, by charges that are delocalized. I'll explain why we call them delocalized in a minute. These don't interfere. In other words, adjacent carbon atoms don't interfere. We make that assumption. It's a big assumption because actually they do interfere, but the results when working with this approximation that we can add the atomic orbitals together, which is the Huckel theory, gives us results that are so near what we get in experiments that everybody accepts, up to, of course, a certain degree of error. If we solve this Schrodinger's equation, we get the E is the energy level, and the energy level is the eigenvalue. So here we have Hx equals lambda x as usual, where psi is the wave function, we call it, which gives us the probability of where the charges will be, of where the electron will be. And the eigenvalues are 2 and 1 repeated twice, okay, 0 and their negatives. And the electrons, here we have 6 delocalized electrons because each carbon atom contributes one electron, will occupy 2 for eigenvalue 2 and the other 4 for eigenvalue 1. That's how the chemists look at it. Okay, so what you're seeing here, are the charges over here. They're the charges, all right? So over, when we look at that electron, so over here and here, the charges are twice as much as on the other side. Okay, so again, this is how the chemists draw the benzene molecule, which is a hexagon of carbon atoms. And you see the double bonds and the single bonds that actually are not stable in the sense that sometimes this is a double bond and sometimes it's a single bond. So they alternate. And that's what we mean. This is the another symbol of the benzene molecule. And what we mean is that the benzene molecule has 2 sort of clouds above it containing these delocalized electrons. Why? Because a carbon atom has 4 bonds, okay? And this bond is called a sigma bond, which is quite strong, and this bond will also be a sigma bond sometimes. But then there's this other double bond, that electron, that is shared by all the carbon atoms, and all the carbon atoms contribute 1 electron. So we have these delocalized electrons, and Schrodinger's equation looks at these delocalized electrons. Right, in 1987, many of you were not born yet, but just a few years before you were born, I suppose, carbon-60 was discovered. Carbon-60 has 60 atoms. This is the monument to carbon 60 at the Royal Chichele House, Royal Society in England. It's enormous, but it's really beautiful, and it shows you how it goes. So we have a lot of hexagons and pentagons, if you notice. So that's a pentagon, and opposite it, there will be a hexagon. And if we look at Euler's theorem, which says, it says vertices plus faces equals edges plus 2 for a polyhedron. Here faces are pentagons and hexagons, so we have F5 pentagons and F6 hexagons. And if we count the number of edges coming from every vertex, because this is 3 regular, we get 3 edges coming out of every vertex, and therefore 3 times the vertices will count the edges twice. But we can count the edges as well by going around the faces. And when we go around the faces, so we have 5 times F5 plus 6 times F6, we also count the edges twice. And if we solve, we get that F5 is 12. So however large a polyhedron is with pentagons and hexagons only, F5 is always 12. And this is called a fullerene. This is the definition of a fullerene. A fullerene is a carbon, is an all-carbon molecule, which is 3 regular, and it has faces which are just pentagons and hexagons. So if it's 3 regular, we know immediately that its maximum eigenvalue is 3. Because it has pentagons, it's not bipartite, and therefore we know that the minimum eigenvalue will be larger than -3. In fact, it's -2.62. Now, if you put pentagons next to each other, the shape will be very strained and usually breaks down. So we know of no carbon molecules that have pentagons next to each other. Or isolate is this is the same shape, you know, the football have 12 isolated pentagons, 12 5s, 60. So 60 is the smallest stable carbon fullerene. There are many forms of carbon. In particular, we have graphite, which is a conductor, and this is how the molecules look like layers of hexagons that slip over one another. And we know that when we use a pencil, you know how the graphite slips over the paper. It's a conductor. Then we have the diamond, and the diamond is a very strong crystal. All the 4 bonds are used, and it's an insulator. It doesn't allow electrons to flow much. So that's how it goes, right? All 4 bonds are used. We don't have any delocalized electrons. And when the fullerenes were discovered, I saw some fullerene as a blue-gray liquid, and this is how they look under the microscope. Really beautiful. I'm going to end with something I had discovered with Patrick Fowler, FRS of Sheffield University. And it has to do also with the packing in graphs. So we were studying what I had graphs where the eigenvector of the 0 eigenvalue has no 0 entries. In other words, if we look at this as a molecule, each atom in the molecule will be charged. In general, if you take any molecule and there are 0 entries in the eigenvector, that position will not be charged and therefore will not take part in a reaction. But here, each and every atom is taking part in a reaction. I am looking at carbon 36, which, as I had told you, is not very stable because it has pentagons next to each other. And we discovered, do you see the double claw there? A 6. And then you join them into a 3 regular molecule forming carbon 36. And how did we do that? Because we said, can the eigenvectors be 2, 1? You know, can the entries have just 2 and 1? And the black vertices there, at that position, there is an entry 2. At the white vertices, there is an entry 1. And we discovered that for this to happen, the molecule must have a multiple of 6. So this is 6C36. It has 6 of them. Okay. And the smallest one is the Fruchtgraph, which has 12 vertices. So we have 2 motifs joined. This has 6 motifs joined. The Fruchtgraph is also interesting because it's an odd graph. So because it's the smallest, one of 2 smallest isomorphic, it's one of 2 smallest asymmetric graphs. So it has an automorphism group of the identity. Right, I leave you to see this animation. And if you have any questions, I'll be happy to answer.
Thank you, Prof. This was very interesting. Does anyone have any questions for Prof. Sciriha?
By the way, were you listening to me? Because all the time I was getting a note that my...
No, you were...
that was shaky.
There were some jittery points, but most of it was fine, Prof. Does anyone have any questions?
Hello, hi.
Yes.
Xaqt insaqsi ftit. Inti qed tgħid profs li tieħu ż-zero eigenvalue u tara jekk għandek x'non zero jew zero.
Can you speak English because there are Maltese speakers here?
You said that you take the zero eigenvalue and you consider its eigenvector, and you checked in on 0 and 0 components of the eigenvector.
Very good. Are you talking about dimension 1? Right? You're talking about dimension 1. So in other words, there is only one the null space. In other words, for 0 eigenvalue, the dimension is 1. Okay.
Okay. Is there a reason why you take the 0 eigenvalue and you don't consider the other eigenvalues?
Interesting question. Actually, I consider, in general, when I do my research, I consider all eigenvalues. But I started by focusing on the 0 eigenvalue, because the 0 eigenvalue in chemistry corresponds to the Fermi level. That is the level midway between highest occupied orbital and lowest unoccupied orbital. Now, besides this, looking at the 0 eigenvalue just gives you the equation AX equals 0x. So you have AX equals 0, so it's really easy to work with. And it enabled me to find all possible substructures that we need in a graph for the eigenvalue to be 0. So you can take any eigenvalue actually, right? But the difference is that instead of looking at AX equals 0, you will be looking at AX minus lambda I, sorry, you will be looking at A minus lambda I X equals 0. So you bring everything on one side and the theory will be the same. You still have a matrix, but for AX equals 0, we assume a 0 diagonal. And for A minus lambda X equals 0, we assume we have lambda on the diagonal. That's the difference, okay?
So for conduction and insulation, you can consider the other eigenvalues as well?
In fact, yes. Okay. In fact, we do. We have studied what happens if we bombard a molecule with an electron at a certain energy. The energy may be one of the eigenvalues, or it may not be one of the eigenvalues. And we found out that when we do that, the fractions of the charges will flow at the different eigenvalues.
Okay, at the eigenvalues.
Right, at the different eigenvalues. And then when you sum up over, sorry. Okay. Right. Who was asking the question, by the way?
Mark.
Mark.
Mark, yes, Mark. So you were asking about when do we use different eigenvalues? That I answered, right? Yes. And the other one was?
You were telling me that you checked the different energy levels and something happened when the energy level was equal to the eigenvalues, right?
Pardon?
And you are saying that you bombarded the molecules.
When you bombard, is that when you bombard an electron into a molecule, we considered two scenarios. One scenario is to pass through the bonds. Another scenario was that the electron goes at any energy. And we found out that the electron uses the eigenvalue energies, right? Okay. And then when you sum up the contribution at each eigenvalue, you get the total result. And surprisingly, we were getting sometimes insulation, which means that at one eigenvalue counteracts the other from another eigenvalue, you know, and they cancel off sometimes. And this was very surprising given that we have so many delocalized electrons. We were expecting conduction.
All right. Thanks a lot. Thanks.
And in fact, they're equally likely, you know. I mean, conduction and insulation are equally likely. So if you take the molecule and you stick it in a circuit, there are half as many structures that give you conduction as insulation.
If you take random molecules.
If you have
structure.
Right. If you take a random structure, you're likely to get, but there are some that give you conduction wherever you connect. There are some that give you insulation wherever you connect, and there are some that give you conduction or insulation depending on where you connect.
Okay. All right. Yeah. All right. Thanks, Prof. Thank you.